In this video, I'm going to be going over the other naming conventions that we will be using in general chemistry. The first is binary molecular covalent compounds. So this is whenever you have two metalloids, or a metalloid and a nonmetal, or two nonmetals together. And so they'll be in some ratio where you have X at some number and Y at some number. Okay? When you have this, it's important to kind of look at the beginning. Okay? Like, what is the beginning? If it's a metalloid, you got to kind of be careful. There's a couple on there that kind of fall underneath ionic naming conventions. If they're both nonmetals, then you're definitely using binary molecular naming. So it's pretty easy because we have these numbers. We have to indicate the ratio, right? Because I could have NO2, I could have N2O5, I could have NO3. Okay, I can have all of these different little setups, but I don't know which one I'm talking about if I say nitrogen oxide. So what we do is we use prefixes. Okay, so for both of them. For these are Greek prefixes. So mono is 1, di 2, tri 3, tetra, so on and so forth. You don't have to say mono on the first element. You can. I don't care, but you don't have to. So, for example, carbon dioxide is not monocarbon dioxide. Notice for the second element, we use the IDE form. For the first element, we just name it. Okay. The thing to be wary of is watch for metals is an easy way to identify if there is an ionic compound. If there's no metals, don't be confused by polyatomics. These have no charge. Okay? These are covalent bonds. Essentially, think about something like this. If I have Na2SO3, this is sodium sulfite. If I have SO3, this is sulfur trioxide, or monosulfur. Blech. We don't say that though. By the difference, well, this guy right here is SO3 2 minus. So it's important to pay attention to what you're doing. Okay, always include the Greek prefixes with binary molecular compounds. The next class of compounds that we're going to look at is hydrated salts. Again, these are ionic compounds that have water present in the ionic crystal. Okay, they're not in aqueous solution. So the way that you do this is you just name the salt, the ionic component of it, like normal. This is copper 2, or cupric sulfate. And then we need to indicate how many waters are in this formula unit. So we use Greek prefixes and we use the word hydrate. So this is 5, this is pentahydrate. Easy. The last one is a little bit more difficult. So we can kind of see acids for now as starting with a hydrogen. Okay? There's going to be some cases where this isn't true. Okay? The easiest way we can kind of identify if it's an acid for now is it starts with a hydrogen, it has something else attached, it's ionic, and it has aqueous at the end. So, the way that you do this is it's all based on the anion's name. If it ends with IDE, you drop the IDE and you put the anion's name inside of here. So, for example, HCl AQ. Okay, notice it's HCl AQ. HCl gas is hydrogen chloride. HClAq, on the other hand, okay, we see it starts with a hydrogen. It's an aqueous solution. We see the Cl minus. This is chloride, so we use this naming convention right here. We drop the "ide," we add hydroic to it, and we get hydrochloric acid. If it ends in an 8, it's ic acid. Drop the 8, add an ic. If it ends in ite, drop the ite and add an us. So let's go through these really quick. So this is hydroiodic acid. Why? Because it's Hi, starts with hydrogen, is ionic, has aqueous at the end. This is iodide. We drop the IDE, we add a hydroic, boom, there we go. Okay, we start with hydrogen, it's ionic, and it ends with AQ. Cool. So this is nitric acid. Why? Because this is nitrate. This is sulfite. Ends with ite, so we use the us as the AQ. So this is sulfurous acid, not sulfuric. That's different. And then we got HBr. Starts with hydrogen, has ionic bonds. Ooh, but ends with a gas. Therefore, this is hydrogen bromide. So to kind of sum this up, there's some common pitfalls that a lot of students do. There's a lot of M's on the periodic table. There's a lot of C's. Okay, you can't get those confused. Calcium and cobalt and copper and carbon and what else is on there? There's all kinds of C's on there. Manganese, magnesium, mobilium. The M's, they're not all the same. The same thing for the C's. Okay, your carbon is not the same thing as cobalt. Cobalt is not the same thing as copper. Copper is not the same thing as calcium. Okay, so there's a lot of different things you got to be careful for. Do not use Roman numerals when you don't need them. Zinc only has one oxidation state. Therefore, it's just zinc bromide. If you want to watch me trip out, spell fluorine as flowering. It annoys me. Imprecision with your guys that have multiple very closely named bits. Nitride, nitrite, nitrate, right? This is N3 minus, NO2 minus, and NO3 minus. Really gets hairy whenever you get to something like chloride, hypochlorite, chlorite, chlorate, perchlorate. So this is C minus, this is ClO minus, this is ClO2 minus, ClO3 minus, ClO4 minus. Okay. Not balancing, this isn't balanced, right? That's +1 and -2, not balanced. Remember to reduce where you can. Know your Greek prefixes. Do not use Greek prefixes. Here, I'm just going to mention, do not use Greek prefixes, erase that, Greek prefixes with ionic compounds. Okay? So there's a lot of pitfalls. This stuff takes practice. Okay? So what I'm going to do now is I'm going to give you a kind of a flow chart to get you going. It will not work 100% of the time because once you start to get into organic naming, all of this stuff goes out the window because it has a whole different set of naming conventions. And we start to see that acids, there's different types of acids, so on and so forth. So on the next page, I'm going to talk about kind of a flow chart. So when it comes to naming ionic compounds, or inorganic compounds, the first thing we want to look for is, does it start with a metal or ammonium? If it does, we're going ionic. If it doesn't, we're going covalent. Now, does this work 100% of the time? Absolutely not. Okay? That's the way it is. Okay? So this is not a metal or ammonium. It's pretty rare that we see hydronium on the front, but I guess that could happen. But ammonium and metals are the most common. So let's look at if there is, I'm going to zoom out just a little bit, what the next thing to do on the ionic side. Okay. If it has something H2O or says hydrate, then you use hydrate naming conventions. If there's no H2O, that means it's part of the formula, then you use ionic naming. Now, we move over here to the covalent side. We're going to have three different situations that can happen here. So the first two are, does it start with H? Or is it a weak acid? Don't worry about what that means. We'll get to that sooner or later. If not, we'll say no H at beginning. Okay. You do a quick check. Make sure it's only two nonmetals or metalloids. This is a check. Right now, if it was something else, there's no H to begin with, and it wasn't two metals, there's a bunch of other stuff, we would be heading over to the organic side, most likely. Or some very odd naming conventions that you'll see in 1B. If it has two nonmetals or metalloids, then you do covalent naming. The last thing over on this side, is it AQ? Then you use acid naming. If it's not AQ, use ionic naming. So it's kind of just a little flow chart to get you through early naming conventions. I didn't make up these rules, so there's a lot of gray areas on a lot of these, so just be prepared for that. This stuff takes practice, okay? Particularly with the kind of difficult polyatomics.